Okay, so we are sort of done with 12, kind of finishing up. A couple of things we're going to finish talking about, and then we will move on to 14, actually, which is the next organic chapter, and then we'll come back to 13 afterwards. But we were sort of focusing on last time really sort of aldehydes, right, and some ketone action, I think. And remember that the aldehydes have a functional group of the carbonyl carbon there, which is the carbon-oxygen double bond with the hydrogen. Always will be found at the end of the molecule because of the hydrogen that is there. That means that when we name these guys, we do just pretty much just lay up an AL at the end of it. We don't need to give the location of this double bond because it's got to be on one side or the other. So we don't have to include it in the name like we do with, say, alcohols or double bonds or triple bonds. But in terms of numbering, as we talked about other groups that may be present, it should always take the priority in terms of numbering. So whichever side it's on, it should always be carbon number 1 in terms of numbering, again, for your other groups. And we would obviously number the other groups like normal, alphabetical, and give the orders. Ketone has the functional group always of a 3-carbon run somewhere in it. And usually in the center carbon of the 3-carbon run will be the double bonded oxygen or our carbonyl carbon that is there. These guys get really like the ONE at the end of it. And because it needs a 3-carbon run to have the functional group there, you'll never find that carbon-oxygen double bond at the end. It's always got to be at least one inside. As we talked about, right around, really 5-ish or more carbons in this case, you do need to give the location of where that carbon-oxygen double bond is. Again, very much like alcohols and stuff like that, if there's kind of multiple places where it could end up, you do need to include the number of its location. Obviously, it does take the priority as well. So wherever this happens to be located, we do want a number, whichever way we'll give this guy, obviously, the smallest number or the lowest number. And then obviously, once you determine which way you need a number to do that, and also include that in the name, again, with 5 or more carbons, then obviously, again, the groups are named accordingly. We talked about some reactions that these guys do. We're going to talk about a few more in just a second, but remember that we can get our aldehyde from the oxidation really of a primary alcohol, right? So if we take our primary alcohol and oxidize it, we will make that aldehyde group. And remember, it is the aldehyde group here that will be able to go through one more oxidation step. And again, outside of the context of our class, how it gets there, but essentially what gets there is just a oxygen that sort of gets placed always right next to the hydrogen. So we always end up making another organic functional group as a result of an oxidation of an aldehyde, which is a carboxylic acid. And by the way, the carboxylic acid is named OIC acid at the end, basically. And that is sort of the oxidation that occurs here. And it's the definition where we actually gain oxygen in this case. The first oxidation, if you remember, to get it to an aldehyde is basically the definition of losing hydrogen. And then the second one here is basically the addition of the oxygen to get it there. Now, the difference between that and obviously it is our secondary alcohol, right, that we oxidize to get ourselves to our ketone. And it is the ketone that, once again, will not go through another oxidation step, really, because it's missing a hydrogen that's necessary for that to occur. So it will not go through that. So again, I think the point here of the lab this week was to sort of identify aldehydes versus ketones based on using something like, as we talked about, you can use Benedict's reagent, which kind of turns that orangey red. You could also use Tollens, which kind of turns a mirror color. And the way you could know sort of what you started with is if it's a positive test, then you definitely started with an aldehyde. If it's a negative test in the case of the lab there, that would mean that you had a ketone at that point. And like I said, I think maybe there's an iodine test or something that confirm it was a ketone that you might do in that case. How you draw the product there of the carboxylic acid is 100% pretty much everything all the way up that was there originally stays. And really the only thing you need to insert is the oxygen in that spot, and you'll have pretty much the correct structure if it did go through the oxidation step. So much like we talked about, nothing really changes except for one little part. And in the case of the oxidation of the aldehyde to ketone, 100% of what's there stays there in the case, and you actually just insert the oxygen in that spot and you'll have the right structure every time. Any questions on that there? So here's some colors and stuff for the Benedict's test. And again, it's sort of a blue reagent because copper 2 is blue. And it's the copper 2 that gets reduced down to copper 1, which makes this, again, I don't know, in my experience in the lab, it's more of an orangey color than that color there, but it's sort of an orange reddish type color. And again, that would signify our oxidation of our aldehyde. This is glucose, which has an aldehyde group right there on top. And as you can see, even in a crazy looking guy like this guy, everything's exactly the same all the way through here, except that we essentially just threw an oxygen in that one spot and nothing else basically changes. Now, the reduction of aldehydes and ketones basically will take you back to the alcohol. So remember, oxidation and reduction reactions basically occur together. Oxidation goes one way. And if you kind of want to go backwards, you do the reduction reaction. They could also be done here. So if we take our aldehyde, it will go back to our alcohol. And if we take our ketone, it will go back to our secondary alcohol. And just to kind of show you how that works, when we find somewhere I can scribble, let me scribble here. So if we take something like this aldehyde, and if we decide to do the reduction reaction, which is basically adding H2, right? That is a definition of reduction, is basically the addition of H2. So if you remember, the oxidation step basically was we took off the 2 hydrogens, right? And we took off the hydrogen from the oxygen, and we took off the hydrogen from the carbon that was attached to the oxygen. So when we do the reduction, which is basically the reverse of that reaction, it's the exact same thing that happens. So once again, the only part of this molecule, when we take it through a reduction, that will change is right here. And it's basically at this point, they do not have room to accept anything. I didn't draw the 2 dots on the oxygen on both sides there, but the oxygen's got the non-bonding electrons. So we have to kind of make room for it. So kind of like an addition reaction with an alkene. So what happens 100% of the time in this reaction is, as we talked about, you pretty much are gonna just redraw the entire thing exactly the way it is, but you're going to turn your double bond into a single bond, and that's going to make room for everything to come in. So once again, I'll just draw it below it since I ran a room on the right there. You would just copy it exactly the same. Absolutely nothing changes, except I now need to make my double bond into a single bond, and that's going to make room for basically each of those hydrogens to come in. The good news is you're adding 2 hydrogens, so you can't really mess it up. 1 hydrogen goes to the oxygen, so I'll make it red. So 1 hydrogen will go to the oxygen here, and the other hydrogen will go to the carbon. So just like where we took them off of when we do the oxidation step, we put them back on in the exact same spot. And obviously this is our aldehyde, and this is now an alcohol. And this is a primary alcohol, right? This carbon is attached to 1 other carbon. And right, if we oxidize a primary alcohol, it is basically the opposite move would be going in this way, would be the oxidation step, where we take off the hydrogen. So they are basically opposites of each other. So if you have an aldehyde and you throw it through a reduction reaction, you get back the primary alcohol from which it came. And obviously, if you oxidize the primary alcohol, you get the aldehyde. So they're kind of forwards and backwards reactions, if you want to kind of think about it that way. Question on that one there. Now, the ketone works pretty much the exact same way. So if we started with a ketone, so we'll just draw up a ketone here, perhaps. Let's just do this ketone. All right, so if we do this ketone and we do the reduction reaction, which once again is adding H2. Same thing, all the activity in aldehydes and ketones pretty much revolve around this guy right here, where the carbon and oxygen is located, is pretty much where everything happens. So just like in the aldehyde there, we want to make room for those hydrogens to come in. So we're going to make some room for those hydrogens to come in. And basically, I'm just going to copy this entire thing exactly the way it is. And just like above, I'm just going to simply make the double bond into a single bond. And if I do that little move right there, now the oxygen and the carbon have room for each of the hydrogens. And like before, we're just going to put a hydrogen on each of those guys. So we will put our hydrogen here. We will put our hydrogen here. And again, we basically just undone the oxidation thing that we did before. This gives us a secondary alcohol, which again is where that ketone comes from, right? If you oxidize a secondary alcohol going in this direction, you get your ketone and your H2. If you want to put it back together, throw the H2 back onto your ketone, and it's considered a reduction reaction. Any question on those reactions there? So alcohols to aldehydes or alcohols to ketones is an oxidation move, going backwards, aldehydes to an alcohol, and a ketone back to its appropriate alcohol are reduction reactions, basically the opposites of them. Any questions on that there? Okay. So that's the Benedict test. That's the reduction. All right, so why don't you do this one here, draw the product, or I guess draw it, which one you think it will be, of this oxidation that occurs. All right, let's take a look. So if I was given this, like I got right here in front of me, you know, sometimes it's good to know where you're going before you start doing things, but I would try to identify what this is. Hopefully we see this group up here, which tells us it's an alcohol. And it is a primary, secondary, tertiary alcohol. This is a secondary alcohol. The carbon that's attached to the OH is attached to 1 and 2 other carbons. So what I have here is a secondary alcohol going through an oxidation. So just understanding the reaction of what you should get, I automatically should know over here I should get a ketone, which if this was a multiple choice question means I should just choose that one and move on with my life, by the way. But let's say it wasn't a multiple choice question and you needed to draw something at this point. You know, if you sort of understand what you should get, you know, it kind of helps you maybe figure out, even if you're not sure what should come off, you should have an idea what it should look like. But remember, in this type of thing, pretty much all of our alcohols, if you oxidize it, it is basically going to lose H2, is basically the type of oxidation that's going to occur. So really here, the H2 is going to come off like we've been talking about. It will always come off the hydrogen there that's attached to the oxygen. And then it will also be a hydrogen from the carbon that's attached to the oxygen. And in this case, it would be that guy right there. Now that I know what should come off, I could pretty much draw what's left and just take those guys off of my drawing. And if I do that, I'm just going to once again copy exactly what they got written there. I am removing my hydrogens, obviously. And obviously the hydrogens come off. Now we can't leave the carbon and oxygen like that because frankly, it shorts some bonds. So when we take off hydrogen, we usually have to put on a bond in its place. And that is where our double bond goes, which will make it now a ketone because we have now just created obviously a 1, 2, 3 carbon run with a double bond in the middle. So, you know, remember, not much changes. And sometimes it's really helpful to kind of maybe, if you know, like, oh, primary alcohol should give me an aldehyde, or secondary should give me a ketone. It helps focus you on, you know, what you should be ending up with in terms of drawing. So obviously B would be the right one there. Any questions on that there? All right, well, why don't we do this one then? We've got a double oxidation move. Why don't we draw both of the things? So what do you get after this guy goes through one oxidation and then the second? So draw both of them. I feel like my C and B's are in the wrong spot. All right, tell me what B and C would be if I moved them over. Okay, so let's once again look at what we're starting with. So once again, I see an OH, which tells me this is an alcohol. And this is what type of alcohol? This is a primary alcohol. This is the carbon that's attached to it, and it's attached to one other carbon. So it's a primary alcohol. So again, once again, if you understand what you should get as a result of these reactions, it should help you when we oxidize a primary alcohol, we should always end up with an aldehyde. And again, as I just mentioned, alcohol oxidations is we're going to basically lose H2. So that again helps us understand what we should take off. When we go one more step with our aldehyde, like we talked about, that is going to get us to a carboxylic acid, which this oxidation though of the aldehyde is basically we're going to add an oxygen, right? So again, if you sort of have that understanding, it should help you maybe get your pictures down. So I'm going to start with our original picture here, and I'm going to just kind of draw out the last part of it so we can kind of see all the hydrogens and stuff. So what I'll do is I'll throw the OH up on top, and I'll add my hydrogens there. So I just kind of rearranged everything there. So once again, I'm going to go through my process here, and knowing, oh, it's going to be an aldehyde, I need to take off my H2. Once again, the H2 that comes off is exactly like we did before. We're going to take it there from the oxygen, and we're also going to take it from the carbon. It really doesn't matter which one you did, but I'm going to take the bottom one. So my picture will end up like perhaps what we got going down there. And once again, everything there other than what I highlighted is going to stay exactly the way it is. So we will end up with this, that, and that. And once again, the additional thing that I know is once I take off the hydrogen, I need to then put in the bond, and the bond always between the oxygen and the carbon. I have such trouble with that double bond when I do it separately. Maybe a better drawing of a double bond. I'm gonna try it again. Give it the old college try, they say. I'm not know if that's much better, but we'll call that an aldehyde there. There you go. And obviously, if you wanted to, you could add the H2 that came off. But the main thing, obviously, is that. Now, that is obviously our first oxidation step. Because it's an aldehyde, we could take it that second oxidation step. And once again, understanding that I'm just going to add an oxygen here. This case, everything stays, except I'm just going to insert the oxygen there at the end next to the hydrogen. So I'm just going to copy exactly what was there. And remember, this is the spot where I want to insert my oxygen to the hydrogen. And that gives me my carboxylic acid group. So if you understand what a carboxylic acid group is, you just need to draw it at the end, basically. And if you understand what the aldehyde group is, that should always end up at the end as well. And that will give me my carboxylic acid here. So I think it would be kind of, this guy probably is the answer. This would be the first step, and then that would be the second step there. Any questions on those there? Now, in terms of naming, if we were to name these guys here, this is, first guy is 1, 2, 3 carbons, and it's an alcohol. So that is 1 propanol, right? We do have to get the location because the OH group was on the second one. It would be 2 propanol. Coming to our aldehyde, it is still 3 carbons. So this would be propanal, Al. Don't need to give the location of that aldehyde group because it is at the end, but it is carbon 1 if we happen to have anything else attached. And this guy here is also 3 carbons. Preview of the next chapter here, which we'll get into shortly. This would be known as Propanoic Oic Acid. Also don't need to give the location because much like the aldehyde group, the carboxylic acid does need to be at the end because of hydrogen. So it'll never be interior. And it also would be carbon number 1. And if you had other things attached, you would number accordingly, just like you would do in the aldehyde. Any questions on any of those steps there? I don't know how much of that I was sitting in front of it, but let me scoot this way so you can see some of the other things. All right. So with these reactions, as I mentioned before, sometimes people want to do crazy things and funky things and, draw all kinds of weird structures. But as I mentioned a number of times, you pretty much have almost like 98% of the structure right there in front of you. So if you're ever at a loss, start with the structure and try to figure out what you should change. It should just be a small part of it. Again, there's nothing weird things that happen in anything that we deal with in this class. There's no things opening up and closing and stuff like that. Everything's pretty straightforward in terms of what you should produce. Any questions? All right. All right, so let's start with 2-propanol here and draw what you get with the oxidation. And we also talked about the dehydration reaction last time as well. That is when we take out water, right? So I'll throw up there. It sounded good. I'll throw up some 2-propanol for you there so you can start with that. All right, you take it the rest of the way there. So first oxidation, and then starting with 2-propanol, the dehydration. So not a continuation, but 2 separate ones starting with this guy each time. Type of alcohol here, and this guy is connected to 2 carbons. So this is a secondary alcohol, which, as we've been talking about, obviously when it goes through the oxidation should yield you a ketone. And because it's an alcohol going through an oxidation, once again, we know we should take off 2 hydrogens. And it's going to be the same stuff that we did before. So we're going to grab a hydrogen there, grab a hydrogen there, and basically take it off. Everything else stays exactly the same, except for obviously I'm going to remove those 2 hydrogens. And that's going to give me an oxygen here, which, as we did before, we will now need to make this into a double bond to give us a ketone. And obviously we would have some H2, not O, just H2 that comes off there. Although that does look like an O now. Any questions on that particular one there? There we go. All right, so looking at the next one, we're actually going to do a dehydration. So dehydration basically means we're going to remove water. Hydration means you put water on. Dehydration means you basically take water off. So what we're going to do is I'm just gonna maybe redraw this here with all the hydrogen so we can kind of see everything out. Okay. Now, when we put water on, it goes on basically as H and OH is basically how water kind of comes on. So when we take it off, we basically take off both of those things. So always the easiest guy to find would be the OH. So that one is going to go off, right? So that takes care of that part of it there. Now we do need to remove a hydrogen. The hydrogen does not come off the same carbon. It comes off a carbon next to it. So in this case, we have a carbon to the right and we have a carbon to the left of it. And in this case, they all have the same number of hydrogens, which means we could pretty much take it off of any carbon you like. I'm just going to randomly choose the hydrogen over here to take off. But technically speaking, you take off any of the hydrogens on the guy on the right or any one of the ones on the one on the right. You obviously only take one off, not more than that. So since those 2 are the ones that I chose to take off, I am pretty much just going to copy what I got going on there without those guys. And again, nothing else changes. And now when we take off water, you could kind of see that those two carbons from where we took the water off is a little short in terms of bonds. So much like the H2, we need to actually insert a bond there to fix that. And we're going to make that a double bond at that point with the water coming off. And by the way, that is where that alcohol came from, because if you add water to an alkene, you get an alcohol. So we're basically just bringing it back to where it started from. Obviously, if I took a hydrogen off of the guy on the left, the double bond would go to the left-hand side there between those two carbons as well. Any questions on that? So obviously a dehydration of an alcohol here will give us an alkene. Yeah. Any questions on that? Yeah. Yeah. You can. I just ran out of room. So you can put it next to it. It's fine. Yeah. Truthfully, again, I'd probably be more looking for the alkene picture. It'd be nice if you threw it in, but probably the alkene picture is really what I'd be looking for. I was thinking, yeah. Just like above, I would be looking more for the ketone than the H2 and stuff like that. Other questions on that? Any questions on any of these reactions and stuff like this? I hope you could kind of see a pattern here that, you know, there's not a lot changing, and it's just that one little spot that you just have to kind of focus in on. So keep a very narrow focus when you're drawing these things of what changes. All right, good, yes. Right, the structure and name of the organic that you get when you mix with a Tollens reagent. We're not going to do that, but let's just talk about Tollens reagent is the one that we use to identify an aldehyde, right? Because it has the ability to go through that last oxidation step to that carboxylic acid, making obviously that insertion of the oxygen into really your aldehyde sort of group. So really, if we had a question like this without the drawing part, and we just want to know which one should react, should the first one react, which is butanol? What kind of molecule is butanol? It is a aldehyde, right? Because it ends in Al, right? Which means that should react, yeah? So we should get the carboxylic acid from that, which would be butanoic acid. If we drew it, it would look just like butanol with an O in it. How about acetaldehyde? Should that one react? I'm going to say it should, because it has the name aldehyde in it, right? So that's acetaldehyde, which would tell me it probably is an aldehyde. And this one also should react as well. How about ethyl methyl ketone? No, it should not react, because remember, the ketone really lacks the hydrogen that's sort of necessary to insert that oxygen. So it will not go through it. So the only ones that will turn silver, like a mirror, would be A and B here. And the other ones should not obviously turn silver in that particular case. Any questions on that test there? All right. Before we wrap up this chapter completely, I do want to talk about two other types of reactions that aldehydes and ketones undergo. Just to say we did, I suppose. I don't know. All right. So you can actually react an aldehyde or a ketone with an alcohol. Actually, you can react it with two alcohols. So if we take an aldehyde, let's just take a nice simple one, if I could think about it. Let's just do this guy here. So if we take an aldehyde and react it with an alcohol, and we'll just take a nice simple alcohol like methanol here. What is going to happen when you react it with an alcohol, primary alcohol in this particular case, is there's going to be a first step that happens, and you could probably imagine maybe where it happens. If you had to take a guess, where would it happen? The activity would happen in the exact same location we've been talking about. Right there is pretty much what's going to happen. Now, when we add an alcohol in this situation, when you have an aldehyde or a ketone and we add an alcohol, the alcohol here in the first step really comes on in kind of two parts. It comes on with a hydrogen, and the other part is like an oxygen carbon group that comes on. believe it or not, the hydrogen is positive here, and this guy is actually negatively charged when they sort of separate from each other. So at this point, the way the aldehyde is, does it have room to add anything to that oxygen or carbon? Those guys are filled up at this point, right? There's no room for it. So this is kind of like an addition reaction where we need to make room for it to basically come on. And what we're going to do is, like we did before, we're just going to turn that double bond into a single bond to allow a spot for everybody to come in. So what that means is absolutely nothing changes here, except once again, I'm just going to make that double bond into a single bond to allow room for everybody to add in. Now, when we look at the carbon oxygen bond here, it is sort of a polar bond, right? With which part being more negative? The oxygen is more negative, right? It's more electronegative. The hydrogen, the carbon here is actually more positive. And that's kind of an important thing to remember, because if I needed to add an H plus to that spot, would it be attracted to the negative spot or the positive spot? It is be attracted to the negative, right? Opposites attract. So that is where the hydrogen will end up. The hydrogen will end up over there with the oxygen. So I'll just draw it like this. Now, the oxygen carbon part that's left over from the alcohol is actually negative, which would actually be attracted to the positive carbon, right? Opposites attract. And it actually ends up on the bottom here of the carbon like this. So our alcohol sort of adds in two parts. The H and what I like to call an oxygen carbon type part comes into the other carbon here. What we just made here has a kind of a special name. It is what is known as a Hemi Acetal. It is a Hemi Acetal, Hemi really because it has an OH group on top there, and acetal because it came from a aldehyde, basically, is a good way to remember that. And the main components of a hemiacetal are this. If you have perhaps just a picture of one and you're asked, is it a hemiacetal or something like that? It should have off of a carbon, it should have an OH group. It should have this oxygen carbon group that's attached. And to make it a hemiacetal, it also needs this hydrogen. So those are the three main components of what makes something a hemiacetal. By the way, the hydrogen being there tells us that it really did come from a aldehyde there, because that's the hydrogen that we see kind of hanging out. Any questions on that sort of first step? So sometimes what happens in these cases, or a lot of times in these cases, is you don't add just one alcohol to it, but you actually add two alcohols to it. It could technically be two different alcohols, but we'll just continue on. So what will happen now is this hemiacetal that's already sort of absorbed a alcohol can now continue to react with one more alcohol. And it sort of works the same way. You could think of this alcohol as adding the same two things like H plus and OCH3, which is really negative. Now, what ends up happening in this particular case is a little bit different. When you get to the second alcohol that's added, out of all these guys here, this is an OH group, which is also a polar group, right? And the oxygen here is again or negative, which means that our H plus is going to be attracted to that spot. What happens when you have OH and H? It makes two hydrogens and an oxygen make water, basically. So what happens is when that H plus is attracted to the OH, it actually makes water, which frankly is kind of just happy to be, I'll take that guy there, is happy to be by itself. So what happens is when the water is made, it kind of pops off and it just makes water and that OH part comes off. So the result of that is that the water will actually come off here. So that OH and the H from the alcohol will make water and it will come off. And what that means is we could think about this entire thing over and it stays exactly the same. So what we end up getting, I'm just going to draw it below because I'm running out of a little bit of room here. We will have our CH3, our H, and our OCH3. What is left to add at this point is the other part of the alcohol. So this guy here, which is negative, will now go and add right into that carbon. So you'll put on the other oxygen carbon group and you will get, do a different color or do a red here so you can see the difference. You will get this oxygen carbon group that is being added there. And what we just made here is what is known as tal in this particular case. So that is an acetal. Yes. Oh, you mean just on the right hand side there? Yeah, you can put it anywhere you want. I just wrote it first because that's what sort of came off first, to kind of see that. Because truthfully, what really happens, again, outside really the scope of our class, is when that water pops off, what it does is it makes the carbon that's left over there really positive. So that negatively charged oxygen carbon group from the alcohol is now really attracted to it. So it comes right in and attaches at that part. So the main parts of an acetal are this. It is two of these oxygen carbon groups, I like to call it. I have two of them. They basically both came from the alcohol, and it still has the hydrogen. Now, that's the difference between the acetal and the hemiacetal. Is the hemiacetal has only one oxygen carbon group, and it has an OH group. So the end result of this reaction is if you take an aldehyde and add just one alcohol to it, you will produce a hemiacetal, which should have that OH group and the oxygen group from the alcohol being attached. If you take the aldehyde and add two alcohols to it, it will take you all the way down to this guy where you will have two oxygen carbon groups and that hydrogen that will be left over. So if you had, for example, this reaction, and it was like, okay, you're taking this aldehyde and you're adding two of these alcohols to it, and you just want to jump to the end. All you have to do is redraw the aldehyde exactly the way it is and basically put in the oxygen carbon part of the alcohol on both spots, the top and the bottom. And that will get you obviously right to here. So that's sort of the shortcut there. Get rid of the carbon oxygen and just put the two oxygen carbon parts of the alcohol there. And that will shortcut you right into what you get at the end. If you had a reaction where it said, hey, I'm adding two alcohols and I just want what's at the very end of it. Questions on any of those things there? Yeah. That's a shortcut if you had a question where it just was like, here's an aldehyde and you see two alcohols and they want you just to draw what's at the end of it. That will take you to the very end part. Now, obviously, if you had one alcohol, you should stop at this part of it, yeah, at that part. And, you know, you would always have the OH in that case. Yeah. So just adding one alcohol will always result in that hemiacetal, and it always should have that OH group and just the one oxygen carbon group. When I say oxygen carbon group, it's whatever basically is the leftover part of the alcohol after you take the H off of it. That's basically what will be attached to the carbon that was originally in the double bond. So that will always be where it will end up in these guys. Any questions on that there? This exact same setup works with ketones as well, and it's pretty much identical to it, except that, you know, we don't have a hydrogen. We got like an extra carbon group there because it's a ketone. So just to kind of look at what those guys look like, we just take a very simple ketone. And we do the same thing. We're just going to add our alcohol, and we'll do the same sort of simple alcohol here. And if it's a complex alcohol, it's the same. We just have more carbons to draw to the oxygen. So the exact same thing is going to happen here. And again, I'm just going to go underneath it. We're going to take that carbon-oxygen double bond, and we're going to add this alcohol like we did with the other one. And everything will stay the same when we add one alcohol, except that obviously we will make that into a single bond. And just like before, the H is going to be attracted to the oxygen because it's more negative. So the H will end up here. And the oxygen carbon part here will end up on the carbon that was in the double bond down here. And it looks very much like the Hemiacetal, except that it does not have the hydrogen. That's also how you know it actually came from a ketone and not an aldehyde. The aldehyde will always have the hydrogen in this spot. And in this case, you have a carbon group in that spot. And that's, again, how you know it came from a ketone rather than a aldehyde. This also has a special name. Some books call it still a hemiacetal, but some books also call it a hemiketal. Hemiketal because it has the OH group for hemi, and ketal because it comes from a ketone. So that's the way it's sometimes referred to. Just like the previous one, you could add one more alcohol to this guy. And if we added one more alcohol to this guy, it will do the exact same thing as it does in the aldehyde, which is we are going to get our water that's going to be formed and pretty much pop off. So the water, once again, will be the H from the alcohol and the OH there from our. And that will form the water that will come off and now make that carbon really positive there. So that will give us the water that comes off. And now, just like before, everything else here will remain the same. So we could just copy it. And just like before, the only thing left over is this guy, which now will be inserted up there on that carbon. And we end up with, again, a thing that looks very much like an acetal. Again, in the hydrogen here, this is what is sometimes referred to as a ketal. The main parts of a ketal are 2 oxygen carbon groups and no hydrogen. Hemiketal OH group, oxygen carbon group, and again, no hydrogen is the difference there between this and what you get when you have an aldehyde. So with the aldehyde, that hydrogen remains through this reaction. If you start with a ketone, you will not see that hydrogen that is there. Any questions on those reactions? Okay, so that wraps up this chapter here. We will roll into our next organic chapter, final organic chapter of the season. Give me 1 second to find it. It's actually 14. I don't know why in your book they like jump a chapter because 13 is carbohydrates, I think. So we're going to go back to carbohydrates, but I think it's the only book I've ever seen where they break up the organic chapters to throw the carbohydrates in the middle. I don't know why. All right. Let's see here. Do I have that one? I do, I think. Maybe. Will it open? That's the key. It did. What do you know? Lucky, lucky, lucky. There we go. Okay, so we are off to chapter 14 here. Pretty much everything left in the organic basket. Yes. So in this chapter here, we're going to talk about carboxylic acids, esters, amines, and amides. Carboxylic acids have a functional group, as we saw a second ago, of this guy here. Esters have a very similar sort of functional group, but it has a carbon attached. Amines is an NH2 nitrogen. Little nitrogen action happening off of it there. So they're all sort of related to the carboxylic acid with some slight changes that occur in it. And again, those are all obviously the functional groups for each of these guys. Remember, you should be familiar with what the functional groups are. Helps you recognize what you're dealing with. Also should help you recognize how to name things as well. Good. Yeah. All right. So we're going to start with the, what's that? I can. We'll see it again in a second, but there you go. I promise. We'll see it again. Good. Okay. So let's start with the carboxylic acid, which obviously we saw how we can make a carboxylic acid, which is the oxidation of our aldehyde, right? So that is sort of the end product of, if you got way back to the beginning that we talked about there, when you take your primary alcohol like we've been seeing and we oxidize it to our aldehyde, and one more oxidation route there to our carboxylic acid. Again, that is how we make one of these guys. We're basically functional group wise going from an OH to a aldehyde group to a carboxylic acid group or a carboxyl group there. These are the guys, sometimes the formulas are written as COOH, is sometimes how you kind of see that group. When you see the COOH group, it is the carboxylic acid group or carboxyl group, which is this here. So for example, acetic acid is actually one of these guys. And a lot of times acetic acid, which is the major component of vinegar, is written in formula form like that, CH3COOH, and that's really sort of describes it. This group here is like super polar. Yes, it is. We got our carbonyl group. That is the scientific word, superpolar. And that guy is positive and negative. It also has got the one of a kind or two of a kind OH group hanging off of there, which is also very polar. So there's a lot of polarity sort of happening on the carboxyl group. And it makes it very, as we will see and talk about, actually one of the few things that can beat an alcohol in terms of boiling points, because it actually could hydrogen bond with itself in 2 locations, which means it's held together really, really tight and has a very, very high boiling point. Also pretty soluble in water as well, because of that ability to sort of hydrogen bond. But it's one of the few things that has a higher boiling point than like an alcohol does, which it can hydrogen bond just at the OH, but this can hydrogen bond at both of those places. How do we name these guys? Well, we name these guys essentially by, as I sort of previewed a second ago, kind of adding OIC acid to the name. So if we look at this guy down here, which is, if I just throw a CH3 on this right here, which is this guy. If we count up the carbons, it is 2 carbons. And that is based off of ethane. I personally like to just like drop the E and add the oic acid, and it becomes ethanoic acid. So that OIC acid at the end of it. Once again, as I mentioned earlier, you don't need to give the location of that carbon-oxygen double bond, because again, it has to be at the end of the molecule because of the hydrogen. But as we talked about a moment ago as well, we do need to remember that that will definitely be carbon number 1 if there's other things attached and you need to number it. By the way, that is ethanoic acid. That is also acetic acid, which is the same thing. Again, the multiple names are the same thing. And it's basically the major component there of vinegar. This is a sort of line structure of a carboxylic acid, which looks like this with our double bond O. And this guy here has, if we count up our carbons like they did there on the bottom, we got 1 carbon, 2 carbons, and 3 carbons. So 3 carbons is based off of propane, so that will be known as propanoic OIC acid. If you can't recognize the carboxylic acid group in that line structure, it is right here. That is our carbon oxygen double bond down to our OH group there. So that is the functional group of this guy in line structure. We could also have it off of a benzene ring. So once again, this is the carboxylic acid group. And you can see off of the benzene ring, it actually is drawn out to a carbon and the group is kind of like off of the ring there. And again, the major part here would be the benzene ring that we see here. And that is why we kind of start with benzene and drop the E and it becomes benzoic acid. Again, kind of like the OIC acid at the end of benzene, sort of added to it where you drop the E. Any questions on that there? Now, again, if you had other things attached, so let's just say, so let's say we have something like, so once again, if we count up the carbons, we got 1, 2, 3, 4 carbons, which is based off of butane. This right here is our carboxylic acid or carboxyl group. It's really what it's called, carboxyl group. So I counted 4 there. So that's going to become butanoic acid. Now we do have a group that is hanging off of here. So again, although the carbon-oxygen double bond does not need to be sort of numbered in there, that is definitely going to be carbon number 1. That would be carbon number 2. And that means that our chlorine there would end up at carbon number 3. And that would be 3-chloral butanoic acid. So once again, the carbon-oxygen double bond takes the priority in terms of numbering, and any groups attached would be numbered accordingly. Any questions on that there? A lot of these are carboxylic acids, as the name sort of implies, are basically acids. Like, you know, we talked about acid and bases. So they do behave like like regular acids. A lot of them are weak acids, like acetic acid or ethanoic acid. They're sort of weak acids, but they do behave, as we will see, sort of just like acids normally would, which means they typically, an acid is something that donates off, right, an H plus. And it is this H that's attached to the O that is the one that goes for a ride there when it acts obviously as an acid. And again, it's because that OH group is polar, so it allows it to come off a little bit easier. There's none of the other H's there. It's always that H off of the OH in a carboxylic acid that gets used in the sort of acid-base relationship that occurs. So here's, again, a couple of the names here. Obviously, if we have 1 carbon there, it's based off of methane, and that's known as methanoic acid. Ethane based off of ethanoic acid. All right. So once again here, we do want to look for the longest continuous carbon chain. It obviously does need to contain the carboxylic acid group there, or carboxyl group. And if you went straight across, you would have 4. You could also, if you wanted to, went this way because that would contain obviously the group, and it's still 4 if you go that way. So usually like normal, kind of the straightest is the best move. So once again, that is where the butanoic acid part comes from. And once again, here we do have a methyl group that is not part of that. Using our carbon oxygen double bond as number 1, ends up as 3-methyl butanoic acid. Now here we have a benzene ring that has the carboxyl group on it. So this entire thing here is part of the main part of the name, which is the benzoic acid part. This entire thing along with this. So that takes care of all of the benzoic acid part of that name. Now, obviously, you can see we have a couple of other groups that are attached there, and those are a couple of chlorines. So we have a chlorine here and a chlorine there. And because we do have 2 chlorines in the same compound, that is the dichloral part of the name. And because the carboxylic acid group there does take the priority, that is why this carbon it's attached to would definitely be carbon number 1 on the ring. And then obviously our groups there, we would want to go clockwise, as it does give us the smaller numbers. Obviously, if we went counterclockwise, we would end up with like 5 and 6, which is a much larger number. So we always want the smaller numbers. So that is where the 2 and the 3 basically come from here. Any questions on that particular one? So this is a little bit different, and it's an important thing when you look at sort of the benzene ring. And sometimes people will think, well, it's a benzene ring, so I just kind of do like a double bond and like a H off of it, like right onto the ring. So you don't do that. As you can see, you sort of got to attach the whole entire carboxyl group off of the ring there with the carbon that is attached. So here's some names of some of the other ones there: propanoic acid, butanoic acid. These are common names on the right. This is formic acid, and that's acetic acid, propanoic acid, and butyric acid. We will just stay with the IUPAC names of this. I will say formic acid and acetic acid is still used a lot by people. Definitely acetic acid is used, I would say, probably more in normal conversation, in normal conversation you have about these things. It's used in normal conversation more than ethanoic acid. Most people will call it acetic acid. So I would say you should definitely know acetic acid is ethanoic acid, because it is used probably very, very common. And again, it's really the major kind of component of vinegar and stuff like that. So that's really why it's sort of used a lot. So formic acid does come up a little bit as well. So I would say out of these 2 common names, you should be familiar with these, because, in books and sometimes they will kind of use those names a lot because it is a very common name. But for us, if you had either one of these, you should probably lay up these 2 names over here, methanoic acid or ethanoic acid, for it. Any questions on that? So some common carboxylic acids, a red ant sting does contain formic acid. That doesn't sound fun. Obviously, as I mentioned a number of times, our vinegar there is our ethanoic acid. All right, so write the IUPAC name for this guy. And why don't you draw? What do you want to draw there? Why don't you draw 2-ethyl 4-methyl hexanoic acid. Okay, look, we'll start with the one that we need to name. All right, so obviously we want the longest continuous carbon chain. Like everything else here, definitely needs to have our carboxylic acid on it. group 1, 2, 3 for 5 carbons there. And again, that obviously does contain the carboxyl group, which is right there at the end. The only really other option would be to, again, make sure you have the carboxyl group there, would be to start here and go 1, 2, 3. And obviously that is less carbon, so that wouldn't work so well. So we will go with the one I highlighted there, I think the first time, right there. So I'm getting old, but I think I said 5, right? 1, 2, 3, 4, 5. So that is 5 with a carboxyl group. So that is going to then give us a base of the name of Propanoic Acid. Obviously, we can see we got one guy hanging off there at the spot right here. That is a line with nothing at the end of it, right? Which means there's a carbon and 3 hydrogens at the end of it, which means it's a methyl group, right? So again, in line structure, you got a lonely line with nothing at the end of it. It is a methyl group. We know that this for sure here has got to be carbon number 1, which means my methyl group there would be at carbon number 2. So this should be like a 2-methyl Propanoic acid. Any question on that name there? All right, so let's draw the one I made up and we'll hope for the best here. So this is chemistry, I think they say. All right, we'll go that away. I'm not sure yet. Hexanoic acid. So the oic acid tells me it is a carboxylic acid. So I know I should have that group. And because it's a carboxylic acid, I know it's got to be at the end. So I can put that really either end. But more important to sort of start with is the other part of this name, which is hexanoic, which is hexane. So I know that should tell us that is 6 carbons. And much like everything else we've been drawing, that is probably what we just want to start with. And just lay up 6 of those guys there. 1, 2, 3, 4, 5, 6. Again, because it's the oic acid, you need to basically at one end, because it does have to go at the end, you need to put the carboxylic acid group there. And again, you could choose either way because you're drawing it. So it doesn't really matter if you want to put it on the left-hand side or the right-hand side. I'm going to go right-hand side here because I drew that line kind of low there. So I'm just going to throw it over here. So that is my carboxylic acid or carboxyl group really over there on the right. Because I chose to do that, that means numbering wise, that right there should be carbon number 1 for me. So that takes care of this. That means at carbon number 4, I should have a methyl group. So since that is carbon 1, carbon 2 would be next to it, carbon 3, and this would be carbon 4. And we should have a methyl group. And again, if you wanted to draw it below, it's fine, up or down. It doesn't really matter. It's okay. That would take care of that. And at carbon number 2, I should have an ethyl group. So I'm going to go down on this one because I don't have room to go up on top there. So that's a 2-carbon group, which looks something like that, I think. At this point, right, all we want to do now is just add our hydrogens to get everybody to 4 because we're out of name at this point. So if we did that, we'll get rid of our number here so it don't look like anything. All right, we will add our hydrogens in. So starting here, this guy actually has 3 lines, so it needs just 1. This guy here has 2 lines, so it needs 2 hydrogens. This guy has 3, it needs 1. This guy has 2, it needs 2. And this guy has 1, it needs 3 in this case, yeah. So it should look something like that. Yes, sir. Yeah. Are you talking about this group here? Are you when you say 1 at the top, 1 bottom, are you talking like, can you put like a CH2 on the bottom and CH3 on top? Is that what you're asking? No, you can't. You have to keep it together. Yeah, if they're not together, then it's not an ethyl group. And you would have technically something there that would be incorrect because it would just be CH2. It wouldn't have enough bonds. So it does have to stay together. You can, if you wanted to, and I'll just draw that part here. You can, if you wanted to, you know, not write it like condensed if you want, and do like C2H5 or something like that, you know, and just kind of write it like that. You probably wouldn't necessarily do it like that if you're doing kind of condensed formula. You probably would write it more like what we did on the bottom. But that's another way technically you could do that. But they do definitely need to stay together. Otherwise, again, it's not an ethyl group. And what you would have if you split them off is one that's not enough bonds, and you would be left with a methyl group on the other side, which would be a different group. Other questions? Okay. All right, so why don't we name these guys here, see what we come up with. Okay, let's take a look since we're getting to the end here. So longest carbon chain straight across looks like a winner, I think, for us. 1, 2, 3. It also went from the top over as well. So 3 carbons there is going to be based off of propane. We see the carboxyl group there at the end, tells us it's a carboxylic acid. So that will then become propanoic acid. This again would be carbon number 1, which means that carbon number 2, that would be where we find our only group that's here, which is a methyl group to methyl propanoic acid. Any questions on that name there? Okay. Then this is obviously a benzene ring. Carboxyl group on it, which makes it a carboxylic acid. So that entire thing really is our longest carbon chain. So because it's based off of benzene, this then becomes benzoic acid. Obviously, we'd still have one group that's hanging off there. Once again, where our carboxyl group is attached to the ring will be carbon number 1. Going clockwise here should give us the lowest number, which would be 3. And that would then give us 3 bromyl benzoic acid. Yeah. Any questions on any of those names there? All right, we will stop there for today, I think.